So a new interesting reagent and reaction called the hydroboration of alkenes. So it's a two-part reaction here, and it works just like hydration of an alkene. What do we get when we hydrate a double bond? We get an alcohol, right? We add water across the double bond, and we previously saw that when we hydrate a double bond, carbocation rearrangements can occur. What did you learn last time as a means to stop carbocation rearrangements and still get an alcohol? The mercury demercurization. All right, so there's like three reactions that are all similar but different. We have acid catalyzed hydration of a double bond, you get an alcohol. Rearrangements can occur. Then we move on to the mercury demercurization. Does the same thing if you do it in aqueous solution, but stops carbocation rearrangements. Both those have what type of regioselectivity? Starts with the letter M. Don't everybody shout it out. Yeah, Markovnikov. So, chemists need things. We perhaps need an anti-Markovnikov. So I'm gonna just go ahead and draw the product here. It'll be a little funky 5-membered ring. So this is anti-Markovnikov. Normally the OH would go there and the hydrogen would go there. Normally the rich get richer. And this has anti-Mark regioselectivity. And we see something new and interesting occurring here. This is called syn addition. Where we saw with the mercury, we had anti-addition in addition to the Markovnikov regioselectivity. So Mr. Brown won a Nobel Prize for discovering these reagents. And so the first half of the reaction, there's the BF3.THF. We'll see what that is in a second. And you form this intermediate, and then hydrogen peroxide, and under basic conditions, we get this anti-Markovnikov regioselectivity with syn stereochemistry. So what is THF? That's abbreviation for tetrahydrofuran, which is an ether. It's a cyclic ether. And B2H6 is called diborane. It's a dimer of borane, and it's in equilibrium with a small amount of BH3. None of that's really that important to us. It forms this complex, and we just call it BH3THF. The main thing is when you see this followed by the peroxide and base, you want to think, going to hydrate a double bond. It's going to be anti-Markovnikov regioselectivity, and it's going to be syn stereochemistry. All right, so now we can see the rich, we can see the poor, and we can see that the poor got the hydrogen. So there's the anti-Markovnikov. This thing adds the way it does. And so in the transition state, there's a positive charge on carbon. And since alkyl groups are electron donating by induction, this is more stable than this one here. This only has, maybe we can call 2 alkyl groups stabilizing this positive charge, where this one has 1, 2, and 3. So here's the more stable transition state. So the borane likes to go to this carbon, and this carbon gets the hydrogen. We say borane adds to the double bond in a single step, with boron adding to the less substituted carbon and hydrogen adding to the more highly substituted carbon. And then once we have that borane compound, we go ahead and we add some hydrogen peroxide and sodium hydroxide, and this gets oxidized off real easily, puts the OH on there. So we say oxidation of the alkyl borane with basic hydrogen peroxide produces the alcohol. And the orientation is anti-Markovnikov. I like to say that word regioselectivity. So here's my example on the whiteboard. This thing is stabilized by the THF, but here's where this is the business end of the molecule. Comes up here, wants to make this have the positive charge instead of this one, because this one's more highly substituted. And then it adds across that double bond, and then we oxidize the boron away, and we see that it's a syn addition and it's Anti-Markovnikov. Now maybe I imagine the boron coming from underneath. If it came from the top, I'm going to just quickly draw another one of these. So we get a racemic mixture. We get this plus its enantiomer. This thing plus its enantiomer. The hydroboration step adds the hydrogen and boron to the same side of the double bond. That makes it a syn addition event. Where we saw the mercury demercuration, opposite sides of the double bond, we called that anti-addition. And then when its boron is oxidized, the OH will be on the same side. So there's the syn addition. Now let's look at adding a halogen. Mainly these two. We're not going to worry about iodine right at the moment. And notice they've drawn one going up and one going down. So we call this anti-addition. And we form a vicinal dihalide. And we see that it's an anti-addition. So why is it anti-addition? The mechanism should show us. So imagine this big polarizable electron cloud. We can have an induced dipole. Imagine this one's a little more positive. So these electrons jump out and grab that. And notice we get this three-membered ring. Where have you seen a three-membered ring that has a positive charge on it before? Yeah, the mercuration demercuration reaction. So when the second one adds, it can either add to this carbon or that carbon. We don't really care now. They look identical, but it attacks from the back side of this thing. So same type of intermediate, and we call it a halonium ion. The halo for halogen and M for positive charge. So if we get a ring, so sigma bonds can't rotate. So it looks like we're attacking from underneath. Here's our positively charged intermediate. The next one, if we make an attack here, we'll have this one here. So we get a trans dibromide, like 1,2-dibromocyclopentane. And it says plus the enantiomer. That's like instead of attacking here, if it attacked right here, we'd get the mirror image of this thing. So if it attacks here, we get this one. Notice that moves over and it's down. This one attacked here, this would move over and still be down, and then we'd have bromine here and bromine there. That would be the enantiomer. So once we see how that works, we can get something like cis-butene, and we can say, all right, we're going to get this three-membered ring, and then this will come and hit there, or there, giving me two enantiomers. What's this thing going to look like stereochemically? So here's two Fischer projections. So here's something interesting. If we have the trans 2-butene, these are going to end up in the Fischer projection on the same side. Notice now there's a mirror plane. So we just get one product, this meso 2,3-dibromobutane. So maybe in your mind's eye, you imagine this thing being flat and planar, and you put one bromine coming down, the other going up, kind of like this. Now if you rotate this carbon or this methyl group around, so you get a long backbone, and you can visualize this backbone. Remember, in the Fischer projection, vertical lines are going away from you. So right there's one going away from you if you're looking from up here. So then if you rotate this thing down, this thing will pop up and have a dashed line. So let's see if I can rationalize this if I didn't have that slide in front of me. Might want to visualize it like this. I'm going to just slam that into that one there. Then I'm going to come over here, and I want to preserve that methyl group going back, preserve this methyl group coming out, preserve that hydrogen there. I got a carbocation going on. So I said if I choose to look at this right here, I have the bottom part of the Fischer projection going on already. I can stand up here and look down, and I can see that my bromine is over here on this side. The hydrogen's there. So now the thing to realize, I'm going to just keep this going on over here, like what happens when I rotate this methyl group all the way around like that. It might be easier, I'm going to keep it going on. Best bet is to pull out your model kit. Or if you don't like to rationalize those away and like rote memory, you say, well, if these are both on the same side, the way it turns out, these come out on opposite sides. The methyl group are on opposite sides, or the continuation of the alky chain, your bromines show up on the same side. So bromine's a nice and colored liquid. So if we dissolve some Br2 up in, say, carbon tetrachloride, we can test for a double bond in an alkane, or in a hydrocarbon. So here we add a drop, stir it up, and it disappears. So this is a positive test for a double bond. If we drop a drop of bromine in and kind of shake it up, and bromine's kind of dense, so we see no color change. So there must not be a double bond in this test tube. Decolorizing bromine is the chemical test for the presence of a double bond. Halohydrins, what are those? It's where you have an OH and a halide. So we might call this a chlorohydrin, bromohydrin, iodohydrin. How do we form these? We run that reaction we just looked at, but if we do it in the presence of water as a solvent, we get our halohydrin. Water's going to act as a nucleophile. And it says here, this is a Markovnikov addition. The bromide, the electrophile, will add to the less substituted carbon. Well, I'm so brainwashed with the rich getting richer that if I'm not adding hydrogen, Markovnikov addition doesn't mean much to me. So here's the mechanism. Got our double bond. The halogen adds. We have our halonium cation here. So when there's water, water is the solvent. Water hits here, and then water can act as a base and deprotonate this. And so here we have a halohydrin. Markovnikov regioselectivity and anti-addition stereochemistry. So if we get a ring that is can't rotate on us, here we see the anti-addition. The OH is down and the bromine is up, and then we have the mirror image of this thing. If we have hydrogen and one of these expensive metals at a catalyst, palladium, platinum, nickel's not so expensive. We see here that we add hydrogen across the double bond. We can turn an alkene into an alkane, and we call this catalytic hydrogenation when we add hydrogen across the double bond. And it only takes place if we have a metal catalyst. So what does D stand for? It's an isotope of hydrogen, and it's not tritium. It must be deuterium. And D2O you might have heard of. It's called heavy water. It's used in a hydrogen bond. Oh, excuse me, didn't want to say hydrogen bond. I wanted to say hydrogen bomb. What is a hydrogen bomb? Well, it's a nuclear bomb where they pack a bunch of heavy water around it, and then they actually get a fission reaction. The fission reaction actually causes a fusion reaction. A little nuclear chemistry thrown in today. I'll school all those that played hooky. So the deuterium is just put here. They could have put methyl groups. Then I couldn't talk about heavy water and the hydrogen bomb. But what this will show us is the syn addition. The hydrogens are on one side of this cyclohexene. The hydrogen and the alkene are absorbed on the metal surface. Once absorbed, the hydrogen insert across the same face of the double bond, and the reduced product is released from the metal. So the reaction has a syn stereochemistry, since both hydrogens will add to the same side of the double bond. And here's a molecular picture. Here's the pi bond that has an electron density above and below the plane of this ring. It's electrons in this unused p orbital. It's the way we like to think about it. So a metal like platinum has a bunch of big d orbitals, and so here the hydrogen comes down and basically like bonds to the platinum metal. They overlap orbitals, and we can actually imagine the whole surface of this metal being covered with hydrogen, because typically you have the metal and you bubble hydrogen gas through there. This thing floats by this orbital can overlap with these orbitals, and these can just slough off. There you can see one's already sloughed off, and when this orbital comes back out, sloughs off, and there you see the 2 hydrogens stuck on there, and you see that they add to the same side of the ring, and so that's why it's a syn addition. I didn't want to go there. This is where we're going to end today.